Right. So the breakout room should be closed. So welcome back, everyone. So let me make sure the live on YouTube is working. And so great. So everything here is good. So let's quickly look at the schedule before we before we start with the lecture. So we had the first quiz on Monday. I think there were a few kind of things that came up, but I think overall it was so pretty successful. The average grade was pretty high, which is good. Again, this is kind of worth 25% of one of the other quizzes, and there are going to be 6 other ones. So kind of the score is pretty small. I ended up reopening it until midnight, and I think I will continue doing that with the other quizzes. So I will again open them at 2:30, which with about 15 minutes left in the lecture. And then, so I think most of you will finish them within the time of the lecture. This one, the average completion time was like 9 minutes. I think on average, it's going to be something like that. Might be, I'm guessing between 10 and 15 minutes. It's the average time, but you'll still have half an hour from when you start. But I'll keep them open until midnight. The consolation of that is I'm not going to be directly on Zoom the whole time until midnight to answer any questions about the quiz. We'll try and go over them a bit better, to make sure there hopefully aren't too many questions. We'll still try and be available as best we can through through Canvas would be a good mechanism, or the email that's posted on the webpage. I'll be monitoring those and try and get back as quick as I can, but I might have other meetings and dinner and such that will get away from being able to respond immediately. So the other thing, we posted stuff, we asked you to do stuff in math on Canvas, and I think this worked well. Some of you were very familiar with this, others less familiar, but I think you got a chance to get familiar. Just about everyone was able to do something which was clear enough, right? So if I ask you to do something like that, you can write it that way, and then me and the TAs can parse what you've written and kind of and be able to grade that, which is important because a lot of a component of this course will be understanding how to write correctly in the language of mathematics, and that's the right way to do it. In fact, most of the time you do it in LaTeX or something like that. So great. So then we didn't quite finish what I wanted to cover in the last lecture. So we'll quickly finish with a couple of examples, and then we'll jump into Bayes' rule. I'm hoping you've seen Bayes' rule before, but we'll get to this. But we'll actually see a small example with data, where you're actually using this to do some very light data analysis. And then the next lecture, which would be a week from today, because next Monday is Labor Day, we'll kind of go over a deeper example on how to use Bayes' rule for data analysis. And this will kind of set the foundation for kind of almost everything else we do in the course. It won't be necessarily explaining the rules of probability, but this will be underlying kind of a lot of stuff we'll do. So these will be important to spend a couple lectures on this. So okay, so let's get into the lecture, unless there are any kind of structural questions. So great, so feel free to interrupt me or ask in the chat. So okay, so first I just want to start with kind of reviewing an example. And so this will just be an example of like the conditional and marginal probabilities. And I mean, understanding these is kind of important for kind of being able to construct Bayes' rule and such. But so this is, let me start with saying this is an example where there's some student in college who chooses a shirt every day and a pants every day at random from a pile. Okay, so I've known, I was in college, I've been in college, I had a friend who actually operated like this. And so these are two random variables. He kept all his clothes in one pile. When it got stinky enough, he washed everything. Otherwise, he just randomly selected. Okay, and so the shirt could be either green, it could be red, or it could be blue, and the pants could be blue, or the pants could be so white. Okay, and so this is a probability table, and it was not a uniform probability. Maybe there are different numbers of blues or red shirts and something like that. So the probability of getting blue pants and a green shirt was 30%, and white pants and the green shirt was 5%. Getting a red shirt and blue pants was 0.1, 10%. Getting a white pants and a red shirt was 20%. Getting blue shirt and blue pants was 20%, and blue shirt and red pant and white pants has to add it all up to 1, so that should be 15% of the time. Okay, so this is what the example was. And so you know, this is a joint probability now between the probability of picking a color of a shirt and a probability of picking a color of a pants. And as I've constructed this, these are not independent, and they're not all just uniform. So something a little interesting. Okay, so the first thing to see is the marginal distribution. So we want to write down the marginal distribution, f of s, right? There's a joint distribution that's described here of s, the probably density function of them for discrete random variables for the s and p, the shirt and the pants. But for just the shirt, what we do is we add up the columns. So this is 35% you wore a green shirt, 30% wore a red shirt, and 35% wore a blue shirt. Okay, so we just add up these columns here. We just add these up, right? And that's how we get these marginal distributions. It's marginalizing out the pant, so I just add up all the possible choices of that, right? So this is what the marginal distribution was. And then we also wanted to write the conditional distribution. So this will be, say, the probability of wearing a certain color of pants given a color of the shirt. Okay, and so we'll write this as kind of a function in this example of the shirt equals to red. Okay, so let's say now we can say, now condition that the shirt is red, what's the distribution of the colors of the pants? And so that's now going to be this column here. I know we're going to be in this column. Okay, below the line, that's the total probability. And if you remember the law of conditional probabilities, that's just going to be dividing basically these probabilities by the total probability that I'm conditioning on. Okay, which is 0.3. So that means the probability that that the pants equals blue, given given that the shirt is equal to red, is going to be equal to 0.1 divided by 0.3, which is 1/3, and the probability that pants equal to white conditioned on the shirt is equal to red is equal to 0.2 over 0.3, which is 2/3. Okay, great. So again, I have a probability distribution. This is the conditional probability distribution on the pants color, given that I fixed the shirt color. You notice 1/3 and 2/3 add up to 1. Again, this is a probability distribution, discrete probability distribution on the pants, given that the shirt is red. Right. So, okay. So conditional probability distributions and kind of marginal ones. Just marginal, you're adding up along columns, so you're marginalizing out one of the variables by adding all of the possible scenarios. And conditioning is you're basically dividing by the total probability of that scenario, which you get by marginalizing. Find the marginal probability. Okay. Okay, and then I want to give one more example. This I've got a picture preloaded here. This is a very important multi-dimensional joint distribution called that's called the Gaussian distribution. Okay, and so we talk about the normal random variables, and a Gaussian is basically a multi-dimensional normal random variable. So we'll talk about a d-dimensional Gaussian random variable will go from the PDF of it goes from this will be our function f, goes from RD to R. So from d-dimensional space to kind of a value in R, and this is a probability distribution, so integral of it is 1. In the example here, it's in d equals 2. So d equals 2. In the case, note that it's going to turn out that the Gaussian, the one-dimensional Gaussian is equal to the normal that we talked about in both the last couple of lectures, actually. Great. Okay. And so this is generally defined for a value v. I'll write this down general, and we haven't had all the notation needed for this yet, but I'll just write it down for completeness. So this is a normalizing term to make sure the integral of this is 1, and it's the norm between v and some mu parameter, which is the mean. So this norm is with double bars, and we'll talk much more about this in a few weeks. 2 sigma squared. Okay, so this is the Gaussian distribution for d dimensions. Okay, and so it's got, again, some sigma, right? This is the standard deviation. It shows up in these two parts, one for normalizing, so the integral is 1, and one inside of this exponential. And it's also got this mu, which is the mean. So this is the mean, or and this is the standard deviation here. Okay, and it's a little bit easier to see for the two-dimensional case. And now v equals a vector, so it's vx and vy. Okay, and so now it's 1 over 2 pi sigma squared. That's all the normalizing factor is. Exponent, and I'll write this out explicitly, vx minus mu x squared minus vy minus mu y squared. So I add, that's what the norm squared is in this case, divided by 2 sigma squared. Okay, so that's the two-dimensional case, and this is what I've drawn here, this is the example where mu is equal to 3 and sigma is equal to 1. Okay, so I've drawn, you can see the mean is here at the point, the x coordinate is 2 and the y coordinate is 3, and I get this bump, this two-dimensional bump now instead of a one-dimensional bump. And so you can think of this in higher dimensions as well, and we will come back to this in higher dimensions in the course. So we'll see this again and again and again. So this is just the kind of it's important, so I'm showing this now, and we'll come back to this. In fact, later on we'll have it so it's not symmetric. The standard deviation isn't the same in all directions. We'll see that version later on, but we don't need to go into that now. Okay, I'll just mention one. This is a two-dimensional continuous probability density function. So that means the integral is 1, but at any single point, the probability is 0, but I can take the integral of areas. I can do the conditional or the marginal distribution. One super important thing about the Gaussian distribution is that the marginal and the conditional distributions are also Gaussian distributions. So if I project down to a lower dimensional space, or I look at a slice coming through here, these are the conditional and marginal versions of this, they're still Gaussian distributions. It's got this really nice symmetry across not just the X and the Y directions, but actually any kind of basis or any slice through here, it's still going to look like a Gaussian distribution. This is a really important property that will come back and will be important for a bunch of algorithms that we actually use later on. So great. Okay, so these are just refreshing kind of examples I didn't get to about kind of joint random variables, conditional, and marginal distributions. Okay, so if there aren't any pressing questions on this, I'm going to jump into Bayes' rule and we'll start to see how this is used. So great. Okay, so Bayes' rule. Okay, and so this is a rule named after Thomas Bayes. His Bayes has an S in it, so the apostrophe is after the S, in case you're wondering about that. Okay, so and this is a probability, rule of probability. It's about so let's say we have two random variables, and I'm going to name these M. I'm going to name these M and D, and these are going to stand for model and data. And we'll see, I'll explain by the end of this lecture, you'll understand why I'm going to call them model and data, and we'll see that even more in the, throughout the class. Okay, but they're just two random variables. They could be any random variables, and it's just a simple rule about conditional probability, that the probability of the model given the data can be written as the probability of the data given the model times the probability of the model divided by the probability, these are probabilities of the data. Make sure that's clear. Okay, so this is a rule, just like, this is derived directly from the definition of conditional probability. There is you may have heard of a debate between frequentist statistics and Bayesian statistics. It's not about the truthiness or something of this rule. The rule is true. It's about how to use this rule within the modeling of data. We'll be fairly agnostic to those kind of visions within this course. I guess we're going to motivate stuff from the Bayesian perspective, but we're not going to go very, very deep into either of these points of view. So, okay, so let me just kind of spend just to truly drive home that this is just a truth about probability. So let's just derive this. Remember, we have that, we can write that the probability that the model and data is true is the probability that the model given the data times the probability of the data. And this is true from if I were to take this guy and divide through it over here, that's the definition of the conditional probability of the model given the data, right? So this is just a truth, and so I also have that the probability of the model given the data is equal to the probability of, the model and the data is equal to the probability of the data and the model, right? It's symmetric because the set operations are symmetric. And so that means it's also equal to the probability of the data given the model times the probability of the model. Okay, notice the left-hand side of both of these is the same, but the right-hand side is different. Okay, and now what I get is that the probability of the model given given the data times the probability of the data is equal to the probability of the data given the model times the probability of the model, right? I've just set the two right-hand sides equal to each other. And then I solve for, I've divide through by the probability of the data. Okay, so that's Bayes' rule right there. That's it. So I've derived Bayes' rule just by the definition of the conditional random variables. Okay, so this is this is just by definition. It's a cool thing. So why is this? Let me make sure this is clear. Okay, so why is this so important? Basically, what it's going to allow us to do is I basically have the conditional probability of the data given the model on one side and the conditional probability of the model given the data on the other side. It allows me to convert in between these two things. Okay, and we're going to see that the right-hand side looks more complicated, but it's going to be, in a lot of scenarios, going to be easier to compute the right-hand side. I'll actually be able to compute that that's the only way I can get the left-hand side, which is what I actually want. Okay, so that's a short answer. I haven't explained that yet. Well, let me just first go through kind of a very simple example just to verify that this is true. Okay, so let's say I've got a conditional probability table where the model is true or false, and the data equals true or the data equals false. You know, these are two possible events here, say 0.25, 0.5, 0.2, 0.05, right? So this is valid probability table. Okay, and let's compute the right and the left-hand side of Bayes' rule just to confirm that it's true, you know, okay, which is the probability of the model. So sorry, of the data given the model times the probability of the model divided by the probability of the data. Okay, so for the left-hand side here, probability of the model, this is the probability of the model and the data are both true, divided by the probability of the data. The model and the data are both true. This would be 0.25, right? That they're both 1. And the probability that the data is true is the sum of these two things. So that's 0.25 plus 0.75, 0.5. And this is 1/3. Okay, so that's the left-hand side. The right-hand side, of course, is more complicated. The probability of the data given the model is going to be equal to again, the probability of the data and the model divided by the probability of the model times the probability of the model, probability of the data. And this is equal to 0.25, 0.2 plus 0.25, and that's times 0.2 plus 0.25, 0.25 plus 0.5. Okay, and these here are going to cancel out, right? So I'm going to get 0.25 over 0.25 7.5, which is 1/3 again. Okay, great. So unsurprisingly, hopefully, Bayes' rule is still true. Okay, and I can calculate these two sides in different ways. Yeah, this is nothing interesting going on yet. In fact, the right-hand side, which I told you was the useful one, was more complicated to compute than the left-hand side. Okay, so let's go through another example now. It's gonna be a little bit more complicated to kind of illustrate why this can be so powerful. Okay, but everything in this example looks clear. Okay. All right. Okay, so let's talk. This is what I am going to call the cracked windshield example. Okay, and I'm going to have two. I'm going to have a particular event. Okay, I'm going to have an event W that my the windshield on my car was cracked. On the car I own when I was grad school, apparently there was a problem that the windshields were pretty often cracked, and mine got cracked 3 different times over grad school. So it was just, there's some structural issue with this. But let's say, so there's an event W, and let's say the problem lies in the factory which made the windshield. Okay, so then I have a random variable F, which is for the factory. And let's say that F could be in some sample space from 3 factories: factory A, factory B, and factory C. And I want to know which factory was most likely to have been the one that made my windshield, which, given that I know that it cracked, conditioned on the event that my windshield was cracked. Okay. So let's say I know in my region that in my kind of region where I bought the car, I have some statistics on where the windshield likely came from. They're more likely to come closer to where I was, but it depends on the assembly line and, I don't know, some weird stuff like that. Let's say the probability that the windshield was made in factory A, let's say I have this information, that's 50% of the time. Probability that it came from factory B, this happened 30% of the time, and the probability it came from factory C happened 20% of the time. Okay, so it looks like it was more likely it was from factory A, just based on the statistics of where my kind of where I bought the car. Or maybe this is national, like 50% of the windshields of all the cars are made in A and something like that. Okay, but I also have some information saying, well, I've looked this up online and there seems to be a problem. Some of the factories seem to have more cracked windshields than others. Other people have tracked this back. They could happen anywhere. If you hit a rock hits your windshield, it might crack, but it's different at different factories. So at factory A, only 1% of their windshields cracked. At B, though, 10% of the windshields cracked. And at C, it was only 2% of the windshields cracked. Okay, so 10% of the windshields from factory B cracked, but only 1% or 2% from factories A and B. Okay, so now I have this kind of, assuming that the windshield was made in each of the factories, I have this information about this event. Was the probability that this event occurred, would have occurred with that windshield. And so now Bayes' rule allows me to combine these together. Okay, what Bayes' rule in this setting is going to be is the probability, say, of the factory given the windshield cracked was going to be the probability of the windshield given the factory times the probability of the windshield cracking of that my windshield was from that factory, A, B, or C, divided by the probability that the windshield cracked overall. Okay, so I can plug this in for each of A, B, and C, and I have the top two. I don't have the bottom. I don't have what's in the numerator. I don't have the probability that the windshield was cracked overall. Turns out I'm not going to need this. Okay, so the probability that it was an A, that the factory was equal to A, given that it cracked, would be the probability would be, let's see, it's let me just write this out full for A, is the probability that the windshield cracked given it was made in A times the probability it was made in A divided by the probability that the windshield cracked. And in this case, these numbers are 0.01 times 0.5 divided by the probability it was cracked. And this is equal to 0.005 divided by the probability it was cracked. Okay, so I still have this annoying probability that the windshield overall is cracked, but if I do this for each of them, if I do this for B, I'm also going to have that same factor. Okay, so now this is going to be equal to 0.1, because there's a high probability it was cracked if it came from A. 0.3 is the probability it came from A divided by this same factor. Okay, so this is 0.3 divided by probability W, and the probability that it came from factory C is 0.02 times 0.2 divided by the probability is correct, which is 0.004 divided by the probability it was correct. Okay, and so ultimately I'm going to get these three numbers, and they're all going to have the same numerator. Oh, the bottom is cut off. Oh, okay, I see what's happening. Hopefully that fixes it. Thanks. Good. Okay. So I've got these three. There are probabilities so that if I choose the right numerator, these will add up to 1. But what I can do is I can compare the factories, the relative probabilities of the factories. And what I can see is that the factory B can see the volume now. Okay, good. So, oh yeah, so thank you. Factory B there should be a 0 in there. Let me write it like that. Okay, so I still have a 3% or 3 divided by the probability of W for factory B, and 3%, 0.5% for probability for factory A divided by probability it's cracked, and 0.4%. So I've got about like 8 times more likely that it's in factory B, right? So this one, so factory B, given that's cracked, is the most likely factory. So that's what I can tell. B is the most likely factory, even without knowing the total probability is cracked. Okay, I could solve for that. I said the sum of these must equal 1, and then I can solve for the probability of W. I'll leave that for your time for an exercise. Okay, but this is what Bayes' rule allowed us to do. Remember, we're able to do this because we have Bayes' rule here, right? And we're able to take the information. We only had information about the right-hand side, and convert that into the probability of which factory was the source of the problem, given that the windshield was cracked. Okay, this is what we're able to do. Okay, and so this will be more powerful, and this will be kind of the basis of a lot of data analysis, where we replace the idea of a factory. What we want to find out the most likely factory, we want to place it with the most likely model, and the windshield is the data that we have. So we observe a bunch of data, and then we want to find the most likely model, right? We don't care necessarily exactly what the probability is, but we want to find the one that's most likely, given our modeling, kind of given the way we're, of all the models we can consider, find the one which is the most likely to correspond with the data. Great. So let's talk about this a little bit more. Is this the kind of the specifics of this example clear enough? We'll see a couple more examples kind of like this, but in the model and data kind of, if I'm using those words instead.
There's a question in the chat from VJ.
Oh, okay. Oh yeah. So that was a typo which I fixed. Yeah. Oh, can we solve? Do you want to solve for that? Okay. So let's solve for probability of W. What we know is that 1 is equal to 1 over the probability of W times 0.005 plus 0.03 plus 0.004. Okay, right? So those are the three probabilities. I factored out the probability 1 over the probability of W. So I can move this to the right-hand side. Probability of W by multiplying it through, and I'm going to get the sum of these three terms, which is going to be 0.039. Okay, so just under 4% of the time the windshield was cracked. And then if I plug that back into these, I actually get the probabilities. Yeah, so it's going to be quite common that we actually will not be able to solve for this denominator. So as we'll see. You can do it in this scenario, but in the most common scenario we'll use it, we actually won't solve for it. And that's, in some cases, this is kind of a very interesting but very hard problem. In some cases, but often it's just ignored, or we estimate it by samples or something like that. So, okay. Great. So, okay, so what we want to talk about now is this expression, probability of the model given the data. Okay. And so basically, we want to think of this as the data and this as the model. And we want to say we've observed some data and we want to find the most likely model. So this is often called the maximum the maximum a posterior or posteriori. My Latin isn't great, but this is called the map estimate. Okay, MAP. Okay, we can, and there's going to be some space of models we're going to consider. Again, some sample space, but we'll define kind of what these space of models means, but just kind of so that maximizes this quantity. Okay, so we want to find, so that this is going to be a space of models. And so the space of models is going to be like, what problem are you solving? Are you solving regression or clustering or classification? That's basically, and is it a linear model or something else? That's what the space of models means. So we'll come back to this. But Okay, and we'll go through a simple example of what this can mean in this lecture. Okay, so this, we'll call this M star, and we'll use this notation arg max, okay, of all the models in some space of models that maximizes this probability of the model given the data. Okay, and this may not actually always be a probability. It may be a probability density function, but the maximum will still be defined. But I'll just write probability now for intuition's sake, like the discrete example I had. And then next lecture, we'll talk about how to do this with probability density functions, which is a little bit kind of, you just have to be more careful, but intuitively, it's the same thing. Okay. Okay, and this arg max. Okay, so you've probably heard of thinking about taking the maximum of some function, right? That's the value where it's maximized, the maximum value it attains. The argmax actually gives me a model. It gives me the argument which maximizes this expression. Okay, so it's giving me the argument that maximizes this. So it gives me actually the model, not the value of the model. Turns out the value I don't care about so much because I usually have this, I'm dividing by some term that I don't know what the value is. So the actual value of it doesn't matter so much, but the model is what's useful because then I can apply that model elsewhere. Okay. So this is equivalent, right, just by Bayes' rule, the space of models, of probability of the data given the model times the probability of the model times the probability of the data. Okay? And what's going to be pretty important here is that this is also going to be equal to the same model that maximizes this is also going to model the probability of the data given the model times the probability of the model, but I don't have the denominator here. Basically, I can cross this out because this term does not depend on the model. This is the probability that I saw the data which I saw, or that the data existed in this way given some other assumptions about the world. So it turns out to find the best model, I don't need to worry about this denominator, the same way we didn't need to know about the probability the windshield was cracked in the previous example to pick the most likely factory to have caused the crack, to have been the result of the cracked windshield that produced it. To pick the best model, I don't need to know the probability of the data or even know how to really necessarily define that. What is the probability of the data that I saw? I mean, turns out we can sometimes write that down and calculate it, but not always, and that's fine because for the map estimate, we just care about maximizing this, and that term does not depend on the model at all. It only depends on the data. Okay, and so what this expression here, this will often be called the likelihood of the model. And I might write this as the likelihood of M. Right? It's a probability about data and it's given the model, right? But I want to talk about, I care about trying to find the best model. And we're going to assume that data is given to us in some way. So we'll often talk about this likelihood function. Okay, and this other probably the model will correspond with the prior, and we'll talk a little bit more. What is the line below the model? What is the line below the model data? Not able to understand the handwriting. Oh, this says likelihood of model. and that's an L of M. Here, let me just, it's important, so let me just erase this again, hopefully make it a little bit more clear. Likelihood of the model, and that's an uppercase L function of the model. Okay. Yeah, so this is the term when you talk about what's the most likely model. This is the likelihood. That's what I'm talking about. Okay, so we'll come back and think about, and it could be, and then there's this other term here, right? The probability of the model also. Could you briefly explain the argmax one more time? I think I get it. Oh, okay. So let's give an example. Yeah, let me say just one thing quick, and I'll go to the next slide and write it. So probably the model, we might say we may have some prior knowledge that one model is more likely than the other, like that there are more windshields made at this factory than the other factory. And sometimes we have the information, sometimes we don't. And if we don't have it, we basically say, maybe those are all the same and we'll ignore it. So for I think the rest of this lecture, we're going to ignore this term. And then next lecture, we'll go back and talk about how to factor in this term. Okay, so let's go back to argmax, and let me do just a simple example in the next slide. But we're going to kind of just look at find the maximum likelihood model, which is different than the map estimate. The map estimate factors in the probability of the model, which we're going to ignore for today, and we'll come back to that next week. Okay, but let me do an example with argmax. Okay, so it's simpler with sets, although we'll be doing this over continuous spaces. So let's say that there's some set, which is going to be equals to 1, 2, 3. Or let's make them numbers, letters instead, A, B, and C. And let's say we have a function, okay? And this function goes from A, B, and C. This gives 7, this gives 10, and this gives 3. So this is f of x, right? This is a function. Okay, so now the max of f of x is equal to 10, right? That's the maximum value, right? This is the max, but if I want the arg max of f of x, right? And usually I'll write this over a set, say x is in the set S, right? And this can also be x is in the set S. I restrict x to be in the set, for instance, or that could be all the places it's defined. Then the argmax is equal to b. This is the argmax. It's the argument, the value that x takes, which maximizes this function. Okay, and so we would write this, and typical notation would be that this is x star. So you put a star on something when it takes the maximum. It could be the minimum or the maximum, but like usually you still use x star for that. But so that's the element in the set which maximized the function. Okay, and so when we're looking, now we're looking over the space of models, and this could be a discrete in the case of the factories with the windshield, or for more generally in the class, this can be a continuous set of models that we're going to be considering. But you know, and it pretty much works the same way. Okay. Okay, so what does probability of the model mean? Okay, so going back to this. Yeah, so I've not totally explained that yet. I gave an example with the windshield where I said, I have some prior knowledge that say 50% of the windshields are made in factory A, 30% in factory B, 20% in factory C, right? That's some prior knowledge that I have here. And in some case in the models, we'll know in the continuous models, we'll go through some examples about that later. I guess in the next lecture, where we're going to see how that works in continuous models, where that would make sense. But it's a probability distribution. So it could be a table for discrete things, or it could be something like a normal distribution for continuous random variables. And that's what we'll see in the next lecture after this one. So don't worry about that too much now. Just for now, assume that that's a constant. It's the same for all models. And that means we can also factor it out of the argmax, right? If that value is the same for all models, it also, the same model gives the maximum independent of what that value is. Okay, so for now, that's what we'll deal with. Yeah, great. Okay. Okay, good. So let me just quickly say about examples of models and data, and then we'll pick the simplest one, and we'll already go through and see how to solve for this. And then a lot of other things in class are going to look like variants of this. They'll just be more complicated. Okay, so think of a model. Often is going to be some simple kind of pattern, or it's going to be a summary of the data. Okay, and the data, these are often going to be some points in RD, so multi-dimensional points, which we'll see later in the class after we do a little bit of linear algebra first, or just some values, which are going to be in R, just real values typically. They could be discrete values, but typically we'll think of them as real values, and we'll see why that is. Okay, so then examples of models. So we'll basically look at 5 core examples of models in this class. The first one is that M is going to be a single point. So I'm going to say I've got a bunch of data points, and think of these, and they could be in RD, but think of them in one dimension. I want to find a single representative. What's the most likely kind of, let's say I observed a bunch of values with noise. What's the actual value that they actually have when I made the observation? Like I measured how far away something is, and I made a bunch of estimates with the spy finding glass or something. I'm like a caddy. How far is it to the hole that I'm trying to hit the ball to? I can get a bunch of estimates of this. What's the true value? There's some true value. How do I estimate this? Okay, so it's a single point estimate of a bunch of values. There could be, so this is what we'll do the last part of the lecture today. And I'll go through in more detail, but things you may have heard of. So with linear regression, okay? So now the model is going to be the common thing is that the simple version we'll start with is going to be a line in R2. Okay, the model is going to be a line, and the data are going to be a bunch of observations. These guys are the data, these are points, and then we're going to try and measure the error in this way, the vertical error of these points onto the line. Okay, we're going to try and find the best model, which is now going to be a line that fits through this data. Okay, so we're going to solve this problem later in the class, and it's, you know, if you're like, okay, how do I do this through Bayes' rule and all that? It turns out it will actually be pretty easy, and you won't have to go through Bayes' rule. We'll kind of find some shortcuts along the way. Okay, clustering. now the model and the example, there are many versions of clustering, but the one we'll focus on is when then the model is going to be a set of k points. Okay, we're going to have, let's say, 3 points here, and then the data are going to be these points which are nearby each of these. Okay, so instead of a single point that we're going to find k different points, and say each data point is close to one of those points. Okay, we're going to do something called principal component analysis, PCA, and this is kind of like linear regression. In high dimensions, they vary what they mean, but this will be a k-dimensional subspace. Okay, and we're going to have points in RD. So these points are going to be in D dimension, and D is bigger than K. And we're going to find the errors by projecting to the closest point on this line. So we start with data in high dimensions, and we want to find a low dimensional subspace that's close to all the data points. Okay, and the best low dimensional subspace is the model. We'll somehow have to parametrically represent this model and find the one that kind of is the most likely model. Okay, so we will do this later in the semester. Okay, and then the last thing we'll do, linear classification. Okay, and this will be a little bit different than these other things. You're going to have now some data points which are plus, and some other data points which are going to be minus. Okay, and we want to find the model now is some line, so that if I measure the points which are on the wrong side, right? So I want all the pluses on one side, all the minuses on the other side, but I'll make some mistakes, and I want those mistakes to be as small as possible. This is roughly how we'll view linear classification. Okay, and so again, the line that best fits this, that has the least error measured in this way or slightly similar ways, is going to be the best model in this case. Okay, so this model and data kind of pattern fits multiple ways, and you shouldn't totally understand all these at this point. We'll spend basically 3 or 4 lectures on each of these problems. Okay, we're going to start today with this single point example. Okay, and we'll see how it works from the Bayesian perspective, and we'll basically reduce this problem to a simple sum of squares formulation, and then PCA's principal component analysis, just for shorthand for now, and then we'll just look at the sum of squares formulation most of the time later. But we'll know that it will root back to this Bayesian analysis and turns out with Gaussian noise. So, okay, so this is kind of a preview just to get you starting to think in the right way of this model and data kind of setting. Okay, so let's go through this more simple example, or a slightly bigger example with data and models. Before I do that, I want to talk about something called a log likelihood. Okay, so now our setting is going to be m star. We want to find m star, which is the argmax of all models. And this is still the general case before I get into the simple example of the probability of the data given the model. Okay. The maximum likelihood estimator, remember, was this. I've ignored the part, the probability of the model. I've assumed that that was constant. So I've also factored that out. Okay, but it turns out you often want to look at this under a log operation instead of the likelihood. So remember, this guy, this was called the likelihood, or L of M, okay? I want to look at the log likelihood, or I'm going to take a log operation of this. And this will be very important for simplifying expressions, okay? And so what's going to happen is that the arg, or this is going to be equal to the arg max of some space of models of the log, okay, of the probability of the data model, okay? And so log is a function which is monotonic for values which are greater than 0. No, the question is, don't we also need to multiply by the probability of the model? We aren't doing this today. We're assuming the probability of the model is constant, right? So we're going to assume that the probability of model equals probability of model prime for all M, for all of the models, right? So for any model we choose, we're going to get the same value. So we can ignore this part now, and we'll come back to that later. Yeah. So okay, and I've written down a generic log here. I've not told you what the base is. It turns out the base doesn't matter here either. Log is a monotonic function, and converting between bases also does not matter. I can write down that the log of base 1 of x is equal to log of base 2 of x divided by log of base 2 of base 1. Okay, so if I change the base, what is this down here? This is a constant in the change of base. So this is multiplied through. If I change the base of the log, it doesn't affect the arg max again. It affects the value, but not which element of the set of models maximizes it. So I can again ignore what the base of the log is again. In fact, we're going to use the natural log, and we'll see why. We'll tend to use the natural log, but again, it's just a constant factor. So I've just written log for here in this case. Okay, and the log, as it's a probability, so it must be between 0 and 1, or if, in general, it'll be a PDF, so it's going to be greater or equal than 0. And if we assume that the log of 0 is negative infinity, then this is monotonic. So higher values are still higher. So the maximum has the same maximum value. Okay, so great. So I can take this log operator and I can still do this. Okay, so this is going to be especially nice because the log has this property that log of A times B equals the log of A plus the log of B. Why is this important? Because we're going to assume we have independent probabilities here. So we have independent, our data observations are going to be independent, which means their probabilities, we can take the product of them. We can look at just the product of these probabilities, and that's the product on the left-hand side. It turns into a sum on the right-hand side, and a sum will be easier to deal with than a product. Okay. Okay. And so so also I want to say this has a name because I just looked at the likelihood. This will be the maximum likelihood estimate, which is similar to the map estimate, but this will be the MLE. I've ignored the prior term. I've set by this assumption in the top left corner here, I can ignore the prior term. And so I'm just looking at the likelihood function. This is the maximum likelihood estimate, where the map estimate has usually a non-trivial prior. Okay, which we'll deal with next lecture. Okay, great. So this is, I'm gonna look at the maximum log likelihood estimate is what I'll calculate, and this will be we'll see that it's going to be the math will work out in a very nice way. Okay, so let's go through this example now. So my data D is going to be a set of points. Okay, let's say 1, 3, 12, 5, 9. And I'm going to assume that these were drawn independently. So in fact, IID, but I'll explain that in a little bit later, from some normal distribution or Gaussian distribution. We'll typically use Gaussian. Normal is the one-dimensional version, right? With some mu and sigma equals to 2. Okay, so there's actually, we will write this M, this mean, as the model. So this will be, the model will then be this mean point. And I'll assume for now I know the standard deviation. Turns out there are ways to solve for that later, but we'll ignore this, right? So we just want to parameterize the model by that mean point of the distribution. Remember that, so if you draw a picture of what this looks like, there's a point at 1, a point at 3, a point at 12, and 5, and 9. And I'm assuming that there's some sort of model where the standard deviation is 2. And I want to find the most likely model, which is just going to be this point M. The most likely model that these points could have been drawn from this. So all I can do is shift it back and forth, left and right, but I'm fixing kind of the shape of it. And this is a normal distribution. So that means I'm going to write this model down as, this is a function, g of x. So this will be the normal distribution where the mean is the model M, the standard deviation is 2, x. I'll write this as g of x. And if remember, this will be 8 square root of 8 pi, 1 over that. This is the right normalization constant, x, which is e to the power minus 1/8 times the model minus this data point x squared. Okay, so for each data value, which will be a value x, this will be the likelihood. This is the likelihood that given a model M, that I saw this data point x. Okay, so this is given a model, the probably I saw a data point. So this is, I can think of this, I'll write a probability, although it's actually a PDF. Okay, but it's a probability that of data of D equals X given M, given this choice of the model M. That M is equal to, maybe I write mu and plugged in or whatever. Okay. Okay, it's effectively that, but it's actually PDF. No, I factored the sigma in. The 8 is there because it's got a sigma squared in there. Yeah, so the 8 is from the sigma squared. I believe I've worked this out correctly. If not, it's a constant factor. Turns out it's not going to matter. Okay, but this is for one data point x. If I want to write in general the probability of data given this full data set up here, right? Now I want to write the probability of the data given the model. I need to look at all the values that the data can take, which is going to be a product. Just like a sum looks kind of like a sigma, a product symbol looks kind of like an uppercase pi. They're slightly different, but this is a product symbol. So I'm taking the product for all the values of x, which are 1, 3, 12, 5, and 9 of g of x. Okay, and this is equal to the product of x in D, okay, of 1 over 8 pi x over 8th m minus x. Okay, so now I've written down precisely, assuming this Gaussian noise in this data, precisely I want to find the model M which maximizes this expression. Now this looks kind of messy. I'm taking the product of a bunch of things that have a constant factor and an exponential term, and this seems kind of messy, but it turns out that by going through the log likelihood, the math is just going to work out and it's going to be simple. Okay, so in order to find this, I can instead write down the natural log, right? This is the log with base of e of the probability of the data given the model. Okay, this is going to be the natural log of this product x and d, 1 over square root 8 pi x minus 1/8 m minus x squared. Okay, and so remember what we know about natural log. One, we can factor out anything we multiply inside of the log. There's a product there, so we can multiply. There's a bunch of stuff multiplied together. We can turn that into a sum. Okay, and so this will be equal to. So first of all, this whole term I'm going to pull out to the size of sum. So I'll write that second. Okay, but this is going to be a sum over x and d, and I take a log. And the other thing I can do is I can combine together this log and this exponential, and they cancel out. Okay, so this log will cancel out the exponential. So this will be a minus 1/8 of m minus x squared. Okay, so that's the whole exponential part. That's all those terms there. And then I need that coefficient. And there are d of those terms. The cardinality of d, 5 in this case. There are d of those terms, the natural log of 1 over square root 8 pi. Okay, so by taking the log, the formula actually got much simpler. And even better, this term on the right, if I want to take, so in the arg max, I can remove this term, because this term does not depend on the model at all. Okay, it just depends on the count of the data, in fact, right? So I told you it wasn't important, right? So it's not. So how do we turn to a summation at the bottom? Okay, yeah. So we're going to go back through and we're going to use this rule here. This rule about any sort of log. It doesn't matter what the base is. You can take the product of a and b inside the log and turn it into log of a plus log of b. Okay, we're going to use that rule. And if you look inside of this expression at the top here, we're inside of this pink log term, it's a product of all of x and d. And then each term in the product has two parts. It's got the green part, right? So the green part wound up over here. The green part went over there. That's a product, so it's, and then the part inside the exponent, well, the natural log canceled with the exponent, and that went up on the left side. Okay. So it's, it's this log likelihood is doing a lot of work, right? It's taking care of a lot of terms here that are kind of messy, and it turns out that then our goal, we can say that m star is also going to be equal to the arg max of a model from the same space of models, in this case points, right? So in this case, we're just talking about values, real values. So in the space of reals is the space of models. And if we wanted to find the same m stars here, the same that we started with, the probability of the data given the model, we've reduced that to be the same as the sum of x in D, all those 5 data points, m minus x squared. The negative 1/8, yeah, I can put a minus inside of here, but I'm actually going to change this to an arg min because I factored out this minus here. This minus allowed me to turn into a min here. Okay, I factor out the 1/8 because that doesn't matter in the minimum or the max. That's a constant factor. And I go from, if I remove the minus, I'm going from finding the maximum value to the minimum value because I've multiplied by -1. Okay, so now I need to find the arg min of the sum of squared distances. It turns out that this is equal to 1 over the number of data points, this, which is equal to the mean of D. Okay, the point that minimizes the sum of square distances to a set in 1D, turns out also in D dimensions, is exactly the mean. Okay, so, yep.
At the bottom.
Well, yeah, I think I answered, how do we turn into a summation at the bottom? Yeah, so is there another question? Do we need to multiply by sigma in the denominator? Oh yeah, I answered that one too a while back. I think I'm ahead of.
It's hard to see what's at the bottom of the screen. It's just a little bit cut off.
Oh, it's still cut off. Okay, hold on. Let me stop share and reshare again. When I started sharing, my window was partially off the bottom of the screen. Is this better? No?
It's still a little bit cut off.
Huh, okay. I will.
It's not cut off for me.
Okay, it's showing up on YouTube. So that's, I'll try and avoid writing it at the bottom more. Let me, here, what I'll do is I will, let me try that again. For those who might have a problem, let's see if this works. I can. Okay, well, so here's what was at the bottom again. I've copy and pasted that into the next slide. Okay, so and this is, these two steps are both really important, so I'm okay kind of revisiting these again. But so we started with the probability of the day given model, and we assumed the data points were had independent Gaussian noise. And by the independence, so I can take a product because of independence of the noise. I assume they each have independent noise, and I need to make this assumption for any of this to work. Okay, so this is a very common assumption. You assume they have independent noise because it makes this whole math work, and otherwise things are too complicated. Okay, and so then I expanded out what that noise model was. It was Gaussian noise, and I wrote down the expression as the product over these 5 different values of D. And then I took the log of that. So I went from the likelihood to the log likelihood. And by doing, my chat turned off a second. And I can see the questions, I'll get back to them in a second. By going the log likelihood, it turns out that the product, I can use the rule of the sum of terms inside of a log to turn that into a sum. And I've got all the coefficients out on the right, and then the terms inside the exponent where the log and the exponent cancel. And then that's just a sum of square distances. And then I can take the arg min of the sum of square distances, and that turns out that's the mean. Okay, so this is a kind of a really important derivation. Okay, so let's see the questions I missed here. Can that be understood as the discrete expected value of the model? Yeah, this is the most likely model given the maximum likelihood model. Without factoring in a prior, this is the most likely model. This is called the maximum likelihood estimator. So it is the, it's not the expected value of the model. That's going to be something else. And we'll talk about that a little bit more next lecture. I'm not going to detail. Okay, and oh, yeah, so maybe the issue is if you're in full screen on Zoom, it tries to fit the window with the slides, and if your window is too wide, it cuts off the bottom. But if you try and, there may be some settings you can do. Okay. So, okay, great. So good. So I think I'm on top of the questions. We've finished the time for the lecture. This is what I wanted to cover. The proof of why this is the minimum, why the mean is the minimum. It's written in the book. I can stay around afterwards to show it. You need to basically, you take the derivative and you set it equals to 0, and you solve for where it's equal to 0, and it turns out it's the mean. It's a couple lines of algebra. But this is what I want to cover today. We've kind of caught up from being a little bit behind from last lecture. So great. So this is the lecture. All of office hours after if you want to ask me more questions, and then no class next Monday because it's Labor Day. So I'll see you in a week, and we'll go through again a similar example, but a slightly more complicated where we factor in this prior as well. And we'll see it's not really any harder to do, but it'll just give us a chance to kind of see this over again. So if this was kind of a lot going on, that's okay. We'll kind of go through the whole derivation again, basically, in the next lecture in a slightly more complicated version. So, okay, great. And the sum of squared errors that we see here is going to show up throughout the rest of the semester and most of data analysis. So I'll turn off